When an equation is at equilibrium, so we have a reversible equation, then LeChatliers principle can apply to it. LeChatlier, he was a French chemist, and he noticed that in a system at equilibrium, if he changed the concentration, the temperature, or the pressure, he could shift the equilibrium. So he might be able to shift it towards the reactant side or shift it towards the product side, but he could change it. And he actually won the Nobel Prize for this. So remember that in equilibrium systems, only gases and solutions can affect the equilibrium. So solids or liquids, we always ignore. The little catchphrase for LeChatliers principle is add away, take towards. And what I mean by take is by removing a certain concentration that's in the equation. So a shift away from the side added is what will happen. So if you add it to one side, it's going to shift to the other side. Or if you remove something from one side, then the equilibrium will shift towards that side. So again, add away, take towards. So here's a generic equation. It's at equilibrium. I can tell that because of the arrows. And what I'm going to do is I'm just going to add certain chemicals to different sides, and then we're going to look at LeChatliers principle and see what will happen to the equilibrium. So that first one there, it says add A. So if I have this A and B and C and D at equilibrium, if I add A, what's going to happen is there's going to be so much A that the B is going to be able to combine with the A, and it's going to get used up. And so when A and B combined, you are going to get more C and D. So you're going to have an increase in C and an increase in D because A and B are reacting. And because there's so much A, the B actually gets used up with all your collisions. So it's decreasing. So LeChatliers principle, add away. So if I add it to one side, I'm going to shift it towards the other side. So we have a shift towards the products in this case. Let's look and see with the second one. What if I put in a whole bunch of B to this system that's at equilibrium? Well, the same thing that happened before is now going to happen, but with A. So A will be able to make more collisions with B, and when it does, you will increase the amount of C and D. And A, because there's so much B, will get used up, or at least decrease in value. And so you're going to end up with a shift towards the products. You'll end up with more products. Now, what happens if I add something to the product side? What if I put a whole bunch of C into this system at equilibrium? Well, now the collisions with C and D are going to increase because there's just so much C. And you're going to get more A and B because C and D are colliding so much. And then the D is going to decrease because there's so much C and so much more collisions. So you're going to get a shift towards the reactants in this case. So if you add it to one side, it's going to shift it towards the other side. Let's see what happens if I add a whole bunch of D in. If I add a whole bunch of D in, then C and D are going to collide. I'm going to make more A and B. And C is going to go down in concentration because of all those collisions with D. So we're going to get a shift towards the reactant side. All right, so that's the add away part of LeChatliers principle. Let's look and see what will happen if I remove a chemical. So I would maybe add something that would bind up A in this case. And so now B and A can't collide because there's no A because A just got removed. But C and D are still colliding, and they're still colliding, and they are making A and B. So you're going to see B increase, and the forward reaction is not going to happen because there's no A at all for A and B to collide. So you're going to get a decrease in your products. So if you remove something from one side, it's going to shift towards that side. So take towards. So removing from the reactant side will shift it towards the reactant side. What will happen if I remove something from the product side? Well, if I remove all my D, again by maybe adding a chemical that will make a precipitate with D. So now there's no more D. C is still hanging out there, but it can't collide with any D because it's all gone. But the forward reaction is still occurring. A and B are still combining, and when they do, they make C. So C should increase. but A and B are not being made because the forward reaction, the reverse reaction is not occurring. So I'm going to get a shift towards the product side. What will happen if I increase the pressure? If you increase the pressure, you have to look at the number of moles on each side. So on this side, I have 3 moles. And these are all gases, so pressure would apply here. And on this side, I have 4 moles. If you increase the pressure, that means that your volume goes down. So your container is going to be, the space is going to be really, really small. So which would fit better into a small space, 3 moles or 4 moles? And the answer is 3 moles. So in this case, the reactant side has the fewer number of moles, and so it's going to be reactant side. So you're going to go to the side with the fewer moles. And again, that's because your volume is decreasing, and so it will relieve the stress if there's fewer molecules in there. And I'll get fewer molecules on the reactant side. So it just kind of is reaction dependent. So sometimes the product side has less molecules or less moles, and sometimes the reactant side has less moles, like this one. What happens if I decrease the pressure? If I decrease the pressure, I am increasing that volume. So you're going to look for the largest number of moles. So in this case, it's going to be the product side. So because my volume increased, which will fill the space more, well, it's going to be the one with the more molecules. So in this case, it's the product side. So again, it's mole dependent. So you have to count moles. Also, notice that I only have gas species in this equation. If you had any solid particles, remember, solids are not affected by pressure, so you would just ignore those. So don't count them as your moles of gas if it's a solid. And then what would happen if you add a solid or a liquid to the system? And the answer is nothing. Remember, solids and liquids don't affect equilibrium. And so adding a solid or liquid won't change the equilibrium. It'll just stay the same. So here's just a little picture showing the pressure. So again, as you increase the pressure, the volume goes down. And again, it's going to shift to the side that has the fewer amount. And this equation, it happens to be the product side because the product side has fewer number of particles or fewer number of moles. And so it will just fit that space better. If you increase the volume or decrease the pressure, then it's going to shift to the side that has the most moles, in this case, the 4 moles. And so you're going to end up with more reactants in this case. So here are some demonstrations that I did in class. And I failed to mention on the previous slide, what about heat? Well, heat you can treat as a reactant or as a product. So in this case right here, we have heat as a reactant. So this means it's an endothermic reaction. We're adding heat to get the reaction to go. So remember, add away, take towards. So if I add heat to the system of gases, I am going to shift it away. So if I add, I'm going to shift it this way. So I should have an increase on this side and a decrease on this side. And so what's going to happen? Well, it's going to turn a brown color because I shifted to this side. If I remove heat or make it colder, it's going to shift it towards the side that you remove. So remember, take towards. So I am going to end up with a colorless solution if I cool this gas system down. So I'll have an increase in the colorless and a decrease in the brown. So again, treat heat just like it was a product or a reactant, in this case a reactant, and still follow LeChatlier's principle of add away, take towards. Let's look at this one. On this one, we are manipulating our hydrogen ion. And if I add hydrogen ion, it's going to shift it towards the product side. So you should see it turn orange. This is a liquid. So remember, that's not going to do anything. So this will have no effect. Because remember, liquids and solids won't affect the equilibrium. I should have a decrease over here. Let's look at removing. If I remove my ion here, that's take towards, it's going to go this way. This should turn yellow, and this will decrease. So again, add away, take towards, and put your heat in the reactant side if it's an endothermic reaction. If it's exothermic, you would have it on the product side. So in the late 1800s, with fertilizer, it's very, very difficult for the farmers to get fertilizer. So they would use manure from whatever animal they happen to have, horse or cow. They also would take bone and they'd crush it up and they'd add that to their fields. And they'd even take blood from slaughterhouses and put that in their fields. One solution to the fertilizer problem is they would go to these remote islands that it would never rain. It was in a rain shadow, so in an area that it wouldn't rain very often. So off the coast of Chile, there are these islands that it would never rain, and the birds would nest there and basically leave their droppings there for hundreds and hundreds of years. So this picture right here, it looks like just white rock, but that is actually bird guano. So they would take that bird excrement and then they would harvest it. You can see them harvesting it right here, put it in big ships and then carry it to their country. New York had a really big problem because they had so many horses. They had over 1 million horses in the city, and they would leave over 1 million pounds of manure per day. So this is the street piled high with manure. So just the sheer quantity in New York City on the streets and what to do with it and try to get it out to the farms, this was a problem. Before World War I, Germany wanted to be able to not be so dependent on other nations for their fertilizer, because one of the uses for fertilizer was to make weapons. Germany wanted to be more of an active participant in Europe. Germany encouraged its scientists to come up with a way to work with atmospheric nitrogen. Atmospheric nitrogen is N2, and when you look at it, it is triple bonded. Because of that triple bond, it's very difficult to break and use the nitrogen. Not many organisms can use it. We breathe air in and out. We breathe the oxygen just in and out, and we don't use the nitrogen for anything. We take the oxygen from the air and use that, but not the nitrogen. There are some plants that they work with bacteria to fix the nitrogen in their roots. So legumes are types of plants that do this. But pretty much this nitrogen is not able to be used. Well, a scientist by the name of Haber, he came up with a process to use the nitrogen from the air to make ammonia, which is a fertilizer. And in 1913, this scientist, Bosch, he was able to industrialize the process. So take it out of the lab and put it into making ammonia fertilizer in large quantities. With this knowledge, Germany could weaponize its country just using atmospheric nitrogen to make ammonia. And so basically, through chemistry, this caused World War I and then later on World War II. One interesting thing, besides just the sadness of making bombs out of atmospheric nitrogen, is that this increase in being able to make your own fertilizer and not having to depend so much on waste products like manure or having to take a boat to a remote island to fill it up with bird manure, is that it was easier to get the fertilizer to the farmers. And so what we found in the 1800s was a large spike in population because more food could be grown. And in fact, 1/3 of the nitrogen in your body comes from this process that Haber invented. This nitrogen is found in your proteins that you have. Now we have too much fertilizer being produced and we have nitrogen pollution. So this bottom picture shows the Gulf of Mexico, the algal blooms that result from being so much nitrogen. Here is Haber's equation that we have. And notice we have all gases, and notice it's an equilibrium type of reaction. So we have nitrogen from the air, and again, this is triple bonded, and it reacts with hydrogen gas and it makes ammonia. And it is exothermic because we see that heat on the product side. So this is used to make fertilizer, or countries can even use it to make explosives now. But knowing what you know of LeChatliers principle, how can we maximize the amount of ammonia that can be made? So how are we going to make a lot of ammonia? Well, we're going to look at that add away, take towards. We want to always have ammonia being made. So we want to increase the concentration of reactants. So make sure you have lots of nitrogen and hydrogen gas. You can remove the product as it forms. That is the take towards. So it'll keep encouraging making the ammonia. You can remove the heat. This will lower the heat, and again, that take towards, so you'll make more of your product. And you can put this under pressure because on one side I have 4 moles of gas and on the other side I have 2 moles. So if I keep it under a high pressure, it's going to go towards the side with a fewer number of moles. And then the last one is not LeChatlier's principle, but it just makes the whole thing go faster, and that is to use a catalyst. So the catalyst, it's actually a heterogeneous catalyst that's made. So it's just some iron, I believe is what it is, that helps provide landing sites for the nitrogen gas and the hydrogen gas. So kind of a real world application of LeChatlier's principle and how to make fertilizer.